Hi, so welcome again to Moniverse. So today we are going to see the number system conversion, right? So let us get into that. So before getting into the number system conversion, we should know how a number is being represented. Let us consider this example 98.24, in which 98 is called as the integer part, and after the decimal 24 is called as the decimal part. Now, let us see the basic or the common method for converting the decimal to binary or octal. Or now we are going to consider the value xxxx dot zzz to the base 10, which indicates it is a decimal number, to be converted to any of the binary or octal or hexadecimal number system, right? So actually the conversion of this integer part varies from that of the decimal part. So first what we are going to see is the conversion for the integer part. So let us take the integer part separately. So now what we have to do is we have to divide this integer part with the base value of what system we are going to consider. Okay, so this is the thing. So we are going to divide it by y. So while we are dividing, we'll be getting two parts, right? One is quotient and another one is the remainder. So let us consider the quotient as CCCC and the remainder is R. So now to continue this process, what we have to do is we have to check whether this quotient value is greater than the base value y. So once we have checked if this is true, what we have to do is we have to continue the division process, right? So again, we have to divide it by y. So I'm dividing the value by y. Now also I'm getting a quotient and a remainder. Again, I have to go on checking this quotient whether it is greater than y. And I have to continue. So let us consider this value is less than the base value y. So we have to stop it, right? So now we have got remainder 1, remainder 2, and remainder 3. Now we can see how the value has been converted. We have to take the value from bottom to top. That is the value of remainder from bottom to top. So R3, R2, and R1. So this is actually the converted value to the base y. Okay. So this is the general rule for converting any decimal value to octal, binary, or hexadecimal. So, the generally we can just put out the rules that if you are having a number, you have to distinguish between the integer part and the fractional part. And for converting, we need this. So for converting, this is the rule. The rule is the integer part is divided by the base of the number to be converted, and we have to continue the division process until the remainder is less than the divider. So here the divider means the base value of the number which is to be converted, right? And take the we have to take the remainder from downwards to upward, and that will be the answer. So we have now seen how to convert the integer part into the required number system. Now we are going to see how we are going to convert the fractional or the decimal part. We'll be calling the decimal part with the name as fractional part, right? So in this number, the decimal part is VVVV. So it has been considered. And for the integer part, we have considered division. So here, so that is the integer part. We have considered the division for conversion, right? So here we are going to consider multiplication. Okay. So we are going to multiply with a base value, right? So once we multiply, we'll be getting two parts of the number, that is integer part and the fractional part. It can be zero also. This integer part can also be zero, right? We have to consider that. Now, what we have to do is we have to leave this integer part for the next step of multiplication. We have to keep it aside and we have to multiply only the fractional part, right? So what we are going to do is this is kept aside and I'm multiplying this again with a base value. So now I'm getting the second number with integer I2 and the fractional part or the decimal part as BBBB. Next, when I have to stop. So this fractional part usually doesn't become zero for n number of iterations. So you can consider for nth iteration, that is on 4 to 5 times you can do for multiplication if it is not ending with zero, or else if it is becoming zero in the second or third step, you can stop it. So there are two rules for stopping the conversion of fractional part. One is either the fractional part has to become zero, or we have to stop some of the end position, right? So once we have stopped, so I'm getting three integer values, right? So I1, I2. So for conversion, what we are going to do is we have to take the integer value what we got in multiplication from top to bottom. Just recall the things, that is for the integer part we have take the conversion from bottom to top. So here it is completely reversed. That is from the top to bottom we have to take. So now this I1, I2, I3 value will be remaining the converted portion, right? So now we can frame the general rule. That is, as usual, we have to distinguish between the integer and fractional part, and we have to multiply the fractional part with the base. And this multiplication will be giving two parts, that is the integer or fractional or integer and fractional or decimal part, I said, right? Then we have to continue the multiplication with only the fractional part until it becomes zero or to some nth time. Then we have to take the remainder from upward to downward. So the converted value will be coming as a conversion, right? So let us see some examples. First, we can consider for decimal to binary. So binary means the base for binary remains 2. So we have to divide it by 2. So let us have an example of 147 to the base 10. So now I'm going to divide it by 2. So the quotient is, so we have to divide 147 by 2. While I'm dividing 147 by 2, I'm getting the quotient as 73 and the remainder as 1. So now I have to continue the division with the rule. The rule is this 73 has to be, or we can say it is a quotient, right? The quotient has to be always greater than the base value to which we are converting. So here the base value is 2. It should be greater than 2. Yes, it is greater. So I'm going to continue to divide 73 by 2. So now the quotient is 20, sorry, it is 36 and the remainder is 1. So again, it is greater than 2. So I'm going to divide it by 2 again. So it is 18, 0 again. We have to divide 9, 0. Again, we have to divide it by 2 because 9 is greater than 2. So 4 and 1. Again, we have to continue division. So while we are dividing, we'll be getting 2 as the quotient and 0 as the remainder. So with the condition 2 is greater than 2, of course, both are equal. So we have to continue the division. So again, when I'm dividing it by 2, I'll be getting the quotient is 1 and the remainder is 0. So now when I'm checking the condition 1 is greater than 2, the condition becomes false. So I have to stop dividing. So as we have seen the rule, it is the integer part. So, and the division has been stopped. So what I'm going to do is I have to take the values from downwards to upward. So what are the values? Let us take it down. 1, first value. Second value is 0. Third value is 0, 1, 0, 0, 1, 1. And I have converted this into, as I have divided by 2, I have converted this into a binary equivalent number. Okay. So my number is 100, 100, 11. So now we can put the part as 147 to the base 10 as an equivalent value 100, 100, 11 to the base 2. So of course this is the general part. The rule, once again I'm putting the rule. Yes, shall we go to the next one? So here we are going to see the conversion of decimal to octal value. So I'm taking 147 as octal is base 8. I'm going to divide it by 8. So when I'm dividing 147 by 8, I'm going to get the value 18 as quotient and 3 as remainder. So again, the condition is being checked. 18 is greater than 8. Yes, it is true. So I'm going to continue the division. So 18 is going to be divided again by the base value 8. So here we are going to get the quotient as 2 and the remainder also as 2. Now we are going to check the condition. The condition is 2 is greater than 8. It becomes false. So I am going to stop the division and I'm going to take the number from downward to upward. So what is the first number? The first number is 2 and the second number is also 2 and the third number is 3, right? As I have converted it into an octal number, I'm going to write the base as 8. So 147, which is a decimal number, is equivalent to the octal number 223. Now we can go for converting the decimal to hexadecimal. Hexadecimal, the base is 16. So what I'm going to do is I'm going to divide 147 by 16. Okay. So when I'm dividing, I'm getting 9 as the quotient and 3 as the remainder. So now while we are checking the condition 9 greater than 16, it becomes false. So I'm going to stop the division and I'm going to count the number from bottom to top. So the number is 9 and 3. So to the base 16. So this is the answer. 147 will be equivalent to the number 93, which is a hexadecimal number, that is to the base 16. So now we can see the conversion of the fractional parts. So let us consider the number 0.865, which is a decimal number which has to be converted into binary, that is to the base 2. So here the base value is 2, right? So now let us consider this multiplication where the base value is 2 to be multiplied with the decimal part 0.865, and we'll be getting a number which has both integer and the decimal part. So here obviously this integer part will be always either 0 or 1, right? And for the next time, for the multiplication, we have to remove this integer part and we have to multiply only this fractional part. And this multiplication may continue for n times. This n may be always depend upon the number of fractional parts we are having, or we can also extend that, or we can stop in the midst when we are getting this product value, that is the decimal part of the product value, as 0. So there are three conditions there. We have to stop for the nth time, or we have to stop when the decimal parts become 0. So now we can continue. So I'm continuing. I'm getting the answer 1.460. Again, leave this integer part and go for multiplying the decimal part because we didn't get 0, right? So again, I'm getting 0.920. Keep aside this number and we have to go for and we have to continue. So I have continued so many times and we can finish it off because we are having only 3 digits here and we have performed the multiplication for around 6 times. So we can stop it. And now here we have to count the numbers. That is the integer part what we have got for each product from top to bottom, right? So the value can be written as 1, 1, 0, 1, 1, and 1, right? These two ones. So the equivalent of 0.865 will be 0.110111 to the base 2. So this is for the decimal to binary conversion of the decimal part, right? So this is again the rule. So we can now go for converting the decimal to octal. So octal, you all know the octal means 8, right? So here what we are going to do is we have going to take the decimal part and we are going to multiply with 8, the base value, right? So here also the same. The product will be having two parts, the integer part and the decimal part. Here the integer part will be varying from 0 to 7. And we have to multiply only the fraction. We have to leave off this integer part for the second time and third time when we are going. And we have to repeat that for n times, or we can stop when this decimal parts become 0. So the second time I'm multiplying by leaving the 6, I'm getting 7.360. So again, I'm going to continue by leaving the 7. I'll be getting the answer as 2.880. Again, I'm continuing. So let me stop it off. So we have to take the numbers. That is the integer part of these products from top to bottom. So let me take it off. 6, 7, 2, and 7. So as it is a decimal part, I have to put a dot over there. So now 0.865, the decimal number, is equivalent to 0.6727. Now we are going for hexadecimal. As it is a hexadecimal, we are going to multiply with 16. And this integer part of the product will be varying from 0 to 15. Right? The same rule is applicable for all the conversions from decimal to any of the number systems, right? But also I'm going to continue for n number of times, or when the decimal parts become 0, I have to stop it at the mid. So I'm going to continue 13.84 into 16. So we have to discard this 13 and we have to multiply 0.84 into 16. We'll be getting 13.44. Now you have to discard this 13 and you have to go for multiplying for n times. So then we have to take from top to bottom. So now the value is 13, 13, 7, and 0. As it is a hexadecimal number, this 13 will be referring to D. So D70. This will be the answer to the base 16. Now, let us do an example by considering both the integer and the decimal part of a decimal number system to a hexadecimal number system. So initially I'm going to take the integer part. So integer part goes with division, right? And this decimal part goes with multiplication. So I'm taking the first part, 34. 34 divided by 16. The quotient is 2 and the remainder is 2. Now we are going to check it off. This should be always greater than the base value, that is 16. So here the answer goes false. So let us stop it. Okay. So now coming to this one, 4.4674, as it is hexadecimal, the base value is 16. I'm going to multiply and I'm going to take off the integer part of the product. Again, the multiplication for up to 3 or 4 times I can continue, as here there are 4 digits after the decimal. I'm continuing the multiplication for 4 times, right? So now we have to consolidate or take both the answers together. That is for the integer part, I have to take it from bottom to top. So bottom to top is value is 2, 2, and for the decimal part we are going to take from top to bottom. So the value is 0.77. For 10 it is a and 7, right, to the base of 16. So this is the conversion. So hope you all have understood the concepts behind converting a decimal number to various other number systems such as binary, octal, and hexadecimal. Thank you for watching. Let us meet in the next video. Thank you.